So we ran out of time for some things in the review. So these were some questions that were submitted beforehand that I wanted to make sure we talked about. So the first of, and they're all related to dealing with vapor pressure. So they all go together really nicely. So the first one is just reviewing the colligative property of vapor pressure. So one thing to note, because I just copied and pasted this out, so the colligative property, that's where we're going to start to add in our solute. That technically is going to be vapor pressure lowering. So the first question, of course, then is, so what's vapor pressure and why, when you add a solute to it, does the vapor pressure go down? So what's happening is when we talk about vapor pressure, and this is one where when you first learn about it, there's a moment of, what? Huh? Because it's a property of a liquid. And what's happening, though, is we're trying to describe when that liquid goes into the vapor phase. So if you had perfume in a bottle, or if you had isopropyl alcohol, or if you had water in this closed container, some amount of the liquid would go into the vapor phase. So up here is vapor, or the gas phase. Down here is the liquid phase. So some of the liquid naturally evaporates and you get some gas. So this up here we would refer to as vapor or the gas, and essentially how much goes into the gas phase from the liquid is called vapor pressure. So this idea that you're going to have a liquid in a closed container and some amount of that liquid evaporates to a certain pressure, because that's how we get that idea of vapor pressure, is the vapor pressure. So some will go ahead and go into the gas phase. How much goes into the gas phase is determined by the pressure. So vapor pressure then is what describes how much evaporates. So when you have a solute, what essentially happens is, I'm going to use X's, and I know these are kind of dramatic. So when you have a solute, then sure, some of this is dissolved, but some of this is also essentially going to be at the surface. And as that happens, there is not as much availability for the gas to go, for the liquid to go into the gas phase. So we're just not going to have as much of the liquid evaporating because surface sites have been blocked by the solute. So as solute is added, vapor pressure goes down. Now, one of the other interesting things about this is when we are therefore describing, okay, so how much vapor pressure should there still be? How much is present? What we are essentially going to do is we're going to describe the vapor pressure of the solution by describing how much of the original solution of the original solvent is still present. So we're actually going to use mole fraction of the solvent multiplied times the original vapor pressure of the solvent. So essentially what we're trying to do is we're trying to describe how much of the original is still there, how much of the original solvent is still there. So we use the mole fraction of the solvent itself. So the question then is, can we do it with a practice problem? Of course we can, and that's why I have one right here. So we have a solution is 25% by mole, make my life a little bit easier, by mole solvent A. And solvent A has a vapor pressure of 200 torr. The rest of the ideal solution is B, with a vapor pressure of 800. Oh, that should also be in torr. My apologies. What's the vapor pressure of the overall solution? So a few things about this question. One, it told me that it's an ideal solution. An ideal solution, by definition, follows Raoult's law. So this notion of vapor pressure lowering is something that is called Raoult's law, and telling me that I have an ideal solution tells me that I get to use that equation. So ideal solution just means that these do actually mix together. They have similar intermolecular forces that Delta H of solution should be pretty close to 0, and they should mix together beautifully. So this is not an oil and water situation where one's hanging out on top of the other. These blend together and they're miscible in each other and mix together very well. So I want the vapor pressure of the solution. However, I actually have two different liquids each with their own vapor pressure to take into consideration. So this is going to be similar to this equation up here, but the thing is that I have to worry about both solvents, not just one of them. So I'm still going to want the vapor pressure of the solution. And in order to solve for this, what I'm going to do is I'm going to worry about the mole fraction of A and the vapor pressure of A, which is my 200 torr. And then all I'm going to do is add to that my mole fraction of B multiplied times the vapor pressure of B. So all I'm really doing is taking the equation we had originally, and for each solvent, using however much of that we have, multiplied times its individual vapor pressure, and adding them together. So the grand question is, where are these mole fractions going to come from? Well, they gave me 25% by mole. This is not the exact same thing as mole fraction, but it's related to mole fraction in the same way that if we were doing multiplication, we could say that if I wanted to know 25% of a certain value, what we usually do is take 0.25 then of that amount. So I can go ahead and say that what I really have is a mole fraction of 0.25 of A. Just like in percentages, when we add up percentages, my total percentage would be 100%. When we add up fractions, my whole of my fraction is just 1. So therefore, in order to get the mole fraction of B, all I have to do is take 1 and subtract my 0.25 because I'm told that the rest of my ideal solution is B. So therefore, I should have a mole fraction of 0.75 of B. So then this does become just 0.25, so 25% of the vapor pressure of A plus 0.75 or 75% would be the rest of B. Notice that this is all in moles. So I know that usually when we say percent, it's often percent by mass, but the question gave me percent by mole, and that's the reason why I'm allowed to do this, is because the question said this is percent by mole. So that's what I get to use. So then from this I get 50, from this I get 600, and that gives me a grand total of 650 torr. Now the problem should have told me what units it wanted. It did not, so I'm just going to leave these in torr. If on the exam you need to get them into a different unit, in the potentially useful information at the top of the exam, there will be a whole bunch of different conversion factors to go in between torr and atmosphere and millimeters of mercury and all of those. But this is one example of how you might do a problem like this. Remembering that what we need is mole fraction in order to do these problems. Now, the last request in here was to deal with the ideal solutions graph or ideal solution graphs. So what these graphs usually look like is, let's say that, sure, for this exact example, I had 25% by mole A, which means I have 75% by mole B. But what if I was considering doing a different percentage? What if I thought that this vapor pressure was too high and I needed my vapor pressure of my solution to be different? What if I wanted to consider a whole bunch of different percentages or a whole bunch of different mole fractions? Well, what I'm going to do is graph some of my options. So on this graph, what I'm going to do is I'm going to graph the mole fraction of A. That's going to go from 0 to 1. You can pretend that this is actually a percentage, that this is actually 0% and this is actually 100%. All I'm doing is multiplying that by 100%. That's one of the beautiful things about fractions and percentages, is that they interchange very easily. Well, one of the things that the problem, because I'm going to use the same solutions we just talked about, one of the things that the problem told me here is that the vapor pressure of my solvent is 200 torr. So if I had all A, I need to give myself some 2, 3, 4. So if I had all A, if A was the only thing that I had, I would, whoopsies, sorry. No, that happens to me, by the way, in class too. I'm like, let me just erase a little bit. Oh, I did not erase a little bit. There we go. So we're actually going to say that this down here is 200 torr. So notice on this graph that my x-axis is my mole fraction. My y-axis is actually going to be in pressure units. So then what I can do is I can say, okay, so just looking at A, if I have no A in solution, then I would expect the vapor pressure contribution of A to be 0, and there to be no pressure given off by A. If I have all A, then I would expect this to be 200. So because that's the vapor pressure of the pure solvent. So I'm going to have a line that basically is trying to describe the contribution of the vapor of A. But this is going to be a mixture of solutions, a mixture of two. So the other thing that needs to go on this graph, if I have no A, what I'm going to assume is I actually have all B. B, from this problem, we said had of pure, its pure vapor pressure is 800. So therefore on this graph, if I have no A, that means all I have is B. So if I have no A, all I have is B. We could graph that on, we could put that information on the x-axis if we wanted to, but essentially what we're doing is we're saying that for this graph, we have mixtures of A and B. So if I don't have any A, I have to have B because that's the only thing that's represented on the graph. So I don't technically have to tell anybody where the 100% B is. You should know because you have labeled on here where 0A is. Wherever 0A is where you should have all B. So same idea. If I have all B, B's contribution is going to be 800 torr. If I have all A, I should have nothing contributing from B. So I can then also draw a line. Yes, I'm trying to draw a dotted line. It's not going very well. There we go. That's terrible. See if I can get rid of this and draw this a little bit straighter. This is the one hard thing with me doing this in a video setup because we have beautiful versions of these in the notes. That's straighter. That's good. So there's my B line. So I do actually have information about A here in red with the long dashes, and now I have information about B in blue with more of the dots. I did mention when we got started that what the purpose of this would be actually to describe the solution overall. So typically what we also see is we see a third line, and this would actually describe the vapor pressure of the solution. So that's how we get this graph. So usually there's 3 lines in total, one to describe the contribution of the vapor pressure of one solvent, and second line to describe the vapor pressure of the other solvent, and a line on the top where essentially we would be adding these together to describe the overall vapor pressure of the solution. So if we were really good, we could have a point on the graph where, let's see, we were doing 25% A, or that 0.25 mole fraction A. So here on my x-axis, where I'm describing the mole fraction, we're going to assume that this is about the halfway mark. So we're going to assume that this is my 0.25 amount of A. If everything was drawn perfectly, which we kind of know that it's not because I'm trying it by hand, but if everything was drawn perfectly, this point right here would be 50, because when we were doing our math earlier, we had said that 0.25 of 200 torr was 50. So in a perfect world, where the 0.25 of my mole fraction of A would be 50 torr. And if I carried this line up farther, where it hits B, if I came over here, and again, in a perfect world, this would be 600 torr to describe the contribution of B. And if we kept going up, this, we're describing the vapor pressure of the solution, if we came over here, would be 650. Got my own labels are in the way. Would be 650. So, because that's based on the math that we did earlier. So what I'm trying to do is I'm trying to demonstrate what this graph really means based on the math we already did. So if you're wondering where any of these numbers are coming from, what I'm doing is I'm using the problem that we did previously to try to demonstrate how this graph relates to vapor pressure and how the graph relates to Raoult's law. So this particular problem asked about one particular combination of solution. And we can find that particular combination of solution on this graph. That being said, realize that all I did was I took one particular set of data off of this graph, which means this x-axis really talks about a lot of different solutions. So if I picked a different spot over here, and let's say that this is actually 0.9 in A, and I did the exact same thing, this is a completely different solution now. So then this area over here that I'm trying to discuss would be where I would have 0.9 as my mole fraction of A, which means I would have 0.1 as my mole fraction of B. And I have a completely different solution that I'm trying to describe over here on the right. So first of all is to realize that this graph is trying to demonstrate a whole bunch of different solutions and not just one. We usually get used to things where it's like, here is one thing with a bunch of different temperatures and something weird happens to it. And this is actually, here's a whole bunch of different solutions, and here's what happens when you mix different amounts of these two liquids together in different proportions. So that being said, one of the questions we often ask is we often ask things that are trying to investigate what would happen if you had 50% A and 50% B. Now, here's the weird thing. When you say 50% A, this is almost always referring to the mole fraction of the liquid. So oftentimes we'll say words like equal molar amounts of liquid. Equal molar means that the moles need to be the same. Because we're doing everything in mole fraction, that's basically half and half, or 50 and 50, or 0.5 and 0.5. So if we wanted equal molar amounts of the liquid, realize that we're still discussing this x-axis. So therefore, if we want equal molar amounts of the liquid, what we need to find is we need to find the place where there's 0.5 of A, because that's also going to be 0.5 of B, and then the question is then going to be referring to information that's happening here. But reading the problem to realize if it's equal molar amounts of the liquid, that means that you need to investigate the x-axis because that's where the mole fraction information is, and that's where your liquid is. You're going to take a breath because oftentimes people get really entranced by the location where the lines actually intersect. And that's an interesting location. So there's a place over here where my lines actually intersect. The thing with this line is in the vapor phase. So this place could be interesting, but this is actually where the vapor or the gas is equal. Yes, that is equal in pressure. Thinking back to Dalton's law, those equal pressures in that same container will also be equal molar amounts. So the line where they cross is interesting, but that is about the vapor phase, the gas phase. And oftentimes the question is actually asking you about equal molar amounts of the liquid. So whenever you're investigating this graph, just be mindful that you might be asked about the gas phase, or you might be asked about the liquid phase, or you might be given information about one and asked about the other. The last thing I'm going to mention, just because I know folks oftentimes think about this or worry about this, realize that on an exam, we have to usually give you options that you can figure out on your own. So in ALEKS, there's usually a way on graphs that you can like move your mouse and you can get really exact data. You can't do that on our exams. We don't, that ALEKS integration technology is not in e-learning, and we can't do it. So what we can do is we can give you options that are clear enough that you can work with them. So if I wanted to ask you something and you need to tell me information about the mole fraction of A, I have to give you options that are far enough apart that you can pick them. So for example, if I actually wanted to know what is the mole fraction of A where the vapor pressure contribution of A is equal to B, where basically the amount of vapor pressure contribution is the same. That's that point we were talking about where the two lines actually intersect. So the hard thing is that I don't know exactly where this is, but the options that we would give you would be something like this. So I'm asking for the mole fraction of A. You would have options like 0, 1, 0.5, 0.25, and I need some more options, 0.75, and we'll do one more. We'll go with something like 0.1. So we know that the point is over here on the right-hand side of the graph. And while we know it's not all the way over here on the right, so it's not 1, and it's definitely not 0, and 0.5 it's still kind of far away from, the best option is 0.75. Now, you can argue with me that a better answer is perhaps 0.76. You could argue with me that maybe it's a little bit closer to 0.8, or maybe it's a little bit closer to just 0.7. The point, though, is that we typically, if we're going to ask you questions like this, we give you options and you can pick the best option. Sure, maybe it's technically 0.77, but we're not going to make you pick between 0.77 and 0.75 when you're just trying to eyeball something on the x-axis. But you should be able to notice that it's not 1, it's not 0, and it's closer to 0.75 than it is to 0.5. So again, you should be able to figure this out and pick the best answer out of your options. So that's going to be it for my summary on Raoult's law. Yes, there are more questions that we can ask on this style of graph. There always are. This is, if you haven't heard me say it before, I try to never underestimate the creativity of my colleagues. So just keep that in mind, do your best. We have office hours all this week. Be happy to help you guys out if you need more.